A very good morning. The last class we have seen about the economic load dispatch problem. In the today's class, we are going to see about the formulation of the economic load dispatch problem. So once again, so what is the definition of economic load dispatch problem? So it's nothing but optimal allocation of generating units to the generating station which satisfies the demand and also with the minimum fuel cost. So what is the major objective function of economic load dispatch? Major objective function of economic load dispatch is to minimize the total fuel cost involved. Say for example, 3 generating units we have taken, or 10 generating units we have taken. So we have to reduce the total fuel cost of whole generating units. So that is the major objective function of your economic load dispatch problem. So what are the constraints? The constraints are of 2 types. The first one is power balance constraints, and second one is minimum and maximum operating limits. So what is power balance constraints? Power balance constraints is nothing but generation that equals the demand. So whatever the generation that is happening, that is equals the load demand. Okay, load demand or the load. Load is connected to the particular bus system. So what is meant by minimum and maximum operating constraints? So whatever the generation that is happening, that should be, say for example, first generator if you take. So the first generator has to be within minimum and maximum operating limit. So say for example, first generator is 1000 megawatt. So 1000 megawatt means it should be within, say for example, they are giving a limit. You have to operate from 700 megawatt to 1000 megawatt. Second generator is 1500 megawatt. So they are giving a certain limit, like you have to operate that particular generator within like 1300 megawatt to 1500 megawatt. Third generator is 500 megawatt. They are giving the limit like you have to operate between 350 megawatt to the maximum of 400 megawatt or 490 megawatt. So you have to operate within this limit. So what is minimum and maximum operating limits? So whatever the generation that is happening, that should be within the minimum and maximum operating limits. So that is called your like inequality constraint, that is minimum and maximum operating limits. So today we are going to see the formulation of economic load dispatch problem. Yeah. So first, you have already studied in the power system. This is a single line diagram of the whole power generation in the thermal generating. So in the thermal generating unit, generally you have a boiler. Okay. So boiler, in this boiler, enormous amount of heat is given. Okay, via the furnace, enormous amount of heat is given to the furnace. So from this boiler, what will happen is, so superheated steam. So not a normal steam, superheated steam of like 500 to 600 degrees Celsius. Superheated steam is generated. So that is fed to the turbine. Okay, so that is fed to the turbine. So the turbine is coupled with the generator. Okay, so the turbine might be of your own range, like 1000 megawatt, 1500 megawatt, like that. That is of, so whichever the generating unit you are choosing. Okay, so so the thing is that it is rotating that superheated steam is rotating the turbine. That turbine is coupled with the generator. So generator generates the power, and which is given to the bus system or to the auxiliary power system. This is the schematic of the boiler turbine generating unit. This is the schematic of the boiler power generating unit. Yeah. So if you take like generally in the boiler, what is happening? In the boiler, what is happening in the sense, enormous amount of heat is being generated. Okay. So you know like heat rate characteristics. So H is directly proportional to I squared R. Okay, H is directly proportional to I squared R. Okay. So heat rate is directly proportional to the current square. So here the same relation we are using. Same relation we are using like heat rate. H is directly proportional to I square. Okay. So I square resistance is neglected. So H is directly proportional to I square. So in the another terms, in the terms of power, in the terms of power here, so H is directly proportional to P square. So we are taking this term, H is directly proportional to P square. So here in our thermal generating system, so whatever the heat generated, that is equivalent to the power generation. Okay. So if you decrease the heat that is being produced in the boiler, automatically the power generation generation in the the whole system will be reduced. Okay. So say for example you're generating 1000 megawatt of power. So for that 1000 megawatt of power, you have to generate the heat. Then only you at the output you will get 1000 megawatt. So if you reduce the heat, if you are not heating that much coal, you are heating only minimum amount of coal, you are reducing the heat. So automatically what happens is the power generation also will be reduced. So in the another terms, can we use like H is directly proportional to P square. Okay, H is directly proportional to power generation square. But generally, like the power generation, so the heat rate will be reducing always. The heat rate will be reducing. So, say for example, so whatever the heat that is being generated, after sometimes, so at the time of the coal is getting heated, the heat heat generated is maximum. So the power generator also maximum at the some rate automatically. Okay, the heat generator also will be, say for example you are burning some coal, you're burning some coal. So within 5 minutes you will get very good heat. Okay, so within 5 minutes you'll get very good heat. After that, slowly the heat rate get reduced. So for that, what we are doing is the heat rate is reduced. So we are adding this constant. Say for example, at the time of heat generation, at the time of initial heat generation, the H is directly proportional to P squared. After that, the gradually it is decreasing. Okay, so it is decreasing to P, and it is reducing to some other rate. So that rate we are taking as constant. Okay, so now the H is so if you H is directly proportional to P squared plus P plus some constant. So it is the power generation also gradually it is decreasing. Okay, so initially it is the power generation is P squared. So after that, due to the heat reduction, okay, for a certain time, so gradually it is also decreased. So H is directly proportional to P squared plus P plus some constant. Okay, so if you remove that proportionality constant, okay, if you remove that proportionality, so what you will do generally, you will induce some constant. You'll induce some constant in that particular term. Okay, so what we are doing is, so we are removing that proportionality constant. So we are introducing some constant. Okay, A P squared plus B P plus C. Okay, plus some constant like that. So this constant we are taking it as C. Okay, so this A and B and C are called fuel cost coefficients. Fuel cost coefficients. So H is nothing but amount of the heat that is being generated. Okay, so what we are doing is we are removing this proportionality constant. Removing this proportionality constant, proportionality constant. Now we are introducing a new constant term. We are introducing a new constant term that is called A, B, and there's some other constant as C. Okay, so where A, B, and C are the fuel cost coefficients. Okay, fuel cost coefficients. Okay, so next, how to find out? Now we have found out the heat rate. Now, how to find out the fuel cost? How to find out the fuel cost is nothing but the heat rate into the fuel cost. The heat rate into fuel cost is nothing but fuel cost, fuel rate. Okay, fuel rate. So whatever, say for example, the fuel rate is per kilogram is 20 rupees. Say for example 20 rupees. So whatever the heat rate we found out into the fuel cost is nothing but here fuel rate. Okay, the fuel rate. So the same thing. So the cost. Okay, so whatever the cost, say for example 20 rupees into that constant. Say for example AP square plus BP plus C. Okay, so that is nothing but your fuel rate. So generally, if you see this characteristics, okay, heat rate characteristics, so it might be gradually increasing. It might be gradually increasing. So if the heat is increasing, automatically the power generation. So if you take like heat rate characteristics, so in this axis we are taking it as this is the power axis. Okay, power generation axis. So this is the heat rate in MBTU. Okay, MBTU. Okay, it is nothing but million British thermal units per hour. Million British thermal units per hour. So this is the heat rate. Okay, so this is the power generation. Power generation, generally we are dealing with megawatt. Generally we are dealing with megawatt. With the increase in the heat rate, automatically your power generation also is increasing like anything. Okay, so if the heat rate is decreasing, automatically the power generation will be decreasing over here. But here the heat generation, what we are doing is we are increasing over a period of time. Say for example 1 hour, or generally a thermal power station will operate for some 8 hours or 6 hours. So it is, so 6 hours what we are doing is we are constantly giving the heat rate. So if we are constantly giving the heat rate, means automatically your power generation, okay, power generation also will be increasing, gradually increasing. Okay, so that the heat rate it is in million British thermal unit, million British thermal unit per hour. Okay, per hour. So that the heat rate is nothing but your fuel rate. Heat rate and the fuel cost is nothing but the same, because if the heat rate. So whatever so how to calculate the fuel cost? So whatever the heat rate into the fuel rate. Fuel rate, what we are doing is, say for example 20 rupees. In another terms, if you are going with the global market, we are taking that as dollars, because the oil how we are purchasing in dollars. So recently only we are purchasing in rupees. So previously, so global. So if you take majority of the companies, they are buying the oil in dollars only. Majority of the countries, if you take majority of the countries, most of the countries, like 180 countries, they are buying the oil in the dollars only. So in the universal language, we are taking it as dollars per hour. So if you take like in our country, we are buying now recently we are buying the fuel in rupees. So rupees. So you can also take it as dollar per hour or rupees per hour. So whatever the data that is given in the problem, you can take. Okay, generally it might be in rupees, dollar per hour. So if you want to convert that into rupees, the dollar to rupee conversion, that is approximately 78 or 80 rupees, approximately 80 rupees. You can take in that particular scale. Okay, so that is also that. So it is nothing but fuel cost in rupees per hour. So almost same. Heat rate characteristics and fuel cost is same. It is in the characteristics wise, it is the same. Okay, so here, so whatever the rupees you are spending, say for example, you are spending for generating 1000 megawatt of power, you are spending around 10 lakhs. For example, I'm telling you are spending around 10 lakhs. Okay, so if you are spending around 7 lakhs, so the fuel cost, with integrating all the coal cost, everything, you are taking it as that as 7 lakhs, say for example, for generating 1000 megawatt. Say for example, 10 lakhs. You are reducing that cost. You are reducing that cost to, you are not spending that much. Only you are spending only 7 lakhs. So 3 lakhs rupees is a deficit for you. Okay, optimally you have to use, but in this case you are reducing the fuel cost, and what you are doing is you are less utilizing the coal. Less utilizing the coal means automatically the power generation also will be decreasing. Okay, the power generation also might be decreasing. So whatever the fuel cost you are spending, so that much power you can generate. Say for example, instead of 10 lakh you are spending 15 lakhs, so you can generate extra 500 megawatt. So whatever the fuel cost you are spending, automatically the power generation also will be increasing in this rate. Linear rate, it might be increasing. So this is the this is the minimum power generation, maximum power. As I said, like there should be a minimum power generation rate and as well as maximum power generation rate for a generator. If you choose a particular generator, say 1000 megawatt of generator, you should not decrease. You should not decrease the generation to say for example 800 megawatt to the maximum of. You should not increase. So some limit might be there. So you should not increase that generator to 1050 megawatt, something like that. Minimum and maximum operating limit. You have to generate that particular power within this limit only. So I already said what happens if you generate to the minimum. If you are going beyond the minimum range, automatically your efficiency of the particular generation might be reducing. Particular generator might be reducing. So if you have efficiency reducing means automatically heat loss might be there. Some other losses will be there. Automatically that might be the loss for us. Okay, you're spending more and your efficiency is 50%, 40% means definitely that might be the loss for us. Even like you should not overload the generator. There is some limit. Okay, so 1000 megawatt generator, you can't generate 2000 megawatt. Okay, 2000 megawatt you can generate. You can't generate. So there is some limit for that particular generator. You should not exceed this range, even though that is 1000 megawatt generator. So that is the tolerance limit they will give generally. So that tolerance limit they are giving another 20 megawatt or another 30 megawatt. So you should not go beyond that limit. If you go beyond that limit, automatically the lifetime of the, say for example, you are always going beyond that limit, automatically your lifetime of that particular generator might be decreasing. So the company is claiming like for this many hours, okay, for 10,000 hours or 50,000 hours, that particular generator may run for this many years, something like that. Life might be giving. So your daily you're generating, you're going beyond the generating limits. Going beyond the generating limits means automatically the lifetime of the generator might be decreasing. So that is the very important thing. So in this axis, what we are taking is output power generation in megawatt. Okay, so in this axis we are taking is heat rate in million British thermal unit. Million British thermal unit, that is the unit of the heat rate per hour. Okay, so 1 hour only we are taking per hour. Okay, per hour. So say for example, in this axis you are taking for 24 hours. 24 hours also you can take, or 1 hour also you can take. So but we are taking the heat rate in per hour. 1 hour, 1 hour only we are taking. Okay, you can also take depends on your usage, per 24 hours, per 7 hours, per 8 hours, like that you can take. So heat rate, this characteristics you might have been understand. Okay, so and if you take like the fuel cost of first generator, say for example the fuel cost of first generator. Okay, so in the fuel cost of first generator, we are taking F1 of P1. F1 of P1 is nothing but, so generally, what is the generalized term? So F of P1 is equal to A P1 P squared plus B P1 plus C, some constant C. Okay, so the power generation is decreasing at the gradual rate. Okay, so this is the first generator. First generator's fuel cost is F1 of P1 is equal to A1 P1 square plus B1 P1 plus C1. So for say for example, second generator. Second generator, what is the fuel cost? F2 of P2. So F2 of P2 is nothing but A2 P2 square plus B2 P2 plus C2. So similarly, what is the fuel cost of third generator? Say for example, if you are taking three generators, then F3 of P3 is equal to A3 P3 squared plus B3 P3 plus C3. So again, so what is for a fourth generator? Similarly, for what is for, say for example, we are taking 10 generators as a whole. So 10 generators for this economic load dispatch, or for operating the limits also. So so for 10th generator, F of F10 of P10 is equal to A10 P10 square plus B10 P10 plus C10. Okay, so that is the fuel cost. Fuel cost. So whereas what is this A1? Okay, what is this A, B, and C is nothing but fuel cost coefficients. Fuel cost coefficient A1, B1, C1 are the fuel cost coefficients. Okay, then what is this P? P is power generator, power that is being generated in megawatt. So everything we are dealing with megawatt. Don't take it in the some other units like kilowatt or watt, something like that. All so hereafter, because this is the power generation, no. So if you go to any power generating units, any power generating stations, okay, hydro, either might be of hydro stations or a thermal station, then wind power stations, then solar PV, everything you take. So always that rating of that particular generating station is in megawatt. Okay, so if you go for a hydro power station, that is of 100 into 500 megawatt. If you go to a thermal generating station, installed capacity 4,500 megawatt. So what is the generator that is operating? So that is of 500 megawatt or 1000 megawatt, 1500 megawatt. So everything is megawatt. So similarly, the same unit also we are following. So units are very, very important. Okay, so if you miss the unit simply like that, you're telling like say for example, power P1 is equal to 1000. That is wrong. Okay, so 1000 means it might be of any units, 1000 watts or 1000. So you're not telling exact unit. So 1000 megawatt. So if you are mentioning in 1000 megawatt, so P2, so 500 megawatt. So that is very, very good. So you have to add the units over here. Okay, so say for example, if you are calculating total fuel cost, so we have to add the what are all the fuel cost from the all the generating. Say for example, I'm taking only two generators here. Okay, for example, I'm saying you can also take 10 or 20, 30, 40, 100. So how many generators you are taking into account, that is that much fuel rate, fuel cost you can take. So here only I'm taking only two generators. So generator 1 and generator 2. Okay, so the total, what is the total total fuel cost? total fuel cost F of P. Okay, F of P. So that is nothing but F1 of P1 plus F2 of P2. Okay, so if it is n generating units, so I'm telling some limit like 10, 100 like that. If it is n generating units, say for example 1000 generating units, 10,000 generating units, so that is called like 1 to n. Okay, 1 to n. So we are taking in the common, we are dealing with the common gender. So in the another terms, so f of p1 is equal to summation I is equal to 1 to n, 1 to n fi of pa. Okay, so generalizing, we are generalizing the fuel total fuel cost, generalizing the total fuel cost, that is nothing but okay, summation of I is equal to 1 to n fi of pa. So I say substitute I is equal to 1 up to 10, or substitute n as say for example 100. So what you have to do, so f1 or f1 of p1 plus f2 of p2 plus f2 f3 of p3 f4 of p4 up to f100 of p100. Okay, if you are choosing n is equal to 100, if you are choosing n is equal to, say for example, simple, so we are going for simple thing. If n as number, n is nothing but number of number of generating units operating at that particular load dispatch. Okay, or taken into account, whatever you can take, or particular load dispatch. Say for example, capital N, I'm taking as 3. Okay, so I is equal to 1, 2, 3. So how it will come? The equation will come. How the equation will come? So f of p is equal to f1 of p1 plus f2 of p2 plus f3 of p3. Okay, so that is the total fuel cost. So what is f1 of p1? F1 of p1 is a1 p1 square plus b1 p1 plus c1. So what is f3 of p3? Similarly, A3 P3 square plus B3 P3 plus C3. So that is the fuel cost equation. So fuel cost equation. Okay. So whereas A, B, and C are the fuel cost coefficients. A, B, and C are the fuel cost coefficients. Okay. Say for example, in this example, we are taking the three generating units, and minimum and maximum operating limits. Minimum and maximum operating limits also we have taken. Say for example, first generator we have taken as coal power generating unit. Second generator we have taken as diesel power generating unit. Third generating units we have taken as gas generating unit. So gas generating unit. So first generating unit, what we have given, what the limits we have given, like it has to operate from 70 megawatt to 100 megawatt. So diesel generating unit, what is the limit, the minimum and maximum operating limit we are given? So 20 megawatt to 70 megawatt. Okay, actually I missed this megawatt here, so you have to write. Okay, so next gas power generating unit. So gas power generating unit I am taking as 10 megawatt to 20 megawatt. 10 megawatt to 20 megawatt. So what is the fuel cost of the particular first generating unit of coal fired generating units? So that what I am taking this A1 or A11. It is the notation. It may be differ. Okay, so in some other books it is given as A11. In some other books it is given like A1. In some other books, so it is your own notations. You can also take A11. You can also take A1 also. So nothing wrong in that. So you, or otherwise you can take A1 itself. Why? Because in the previous thing also we have taken like A1. So you can also take like A1. So first fuel cost is A1 P1 square plus B1 P1 plus C1. So second, diesel power generating units. So what is the diesel power generating units? So that is nothing but F2 of P2. F2 of P2 is A2 P2 square plus B2 P2 plus C2. Then what is the gas power generating unit is A3 P3 square plus B3 plus C3. Okay, sorry, B3 plus P3 plus C3. So like that also you can